This is the history of the dynamics. Newton talked about the kinematic and kinetic study of the particle. He introduced the equation of motion by using the inertial law F equal to ma. Euler extended the work of the Newton from the particle to the rigid body. He talked about the angular momentum h and its application in the rigid body. The torque or the moment is equal to the change of the angular momentum with respect to time. So this will be our focus in this study. Next we have Lagrange work, which talk about the energy and work. He showed us that without consider the Newton law, we still can derive the equation of motion from the energy point of view, and this is not covered in this study. Consider a rigid body moving with any general motion in space. By using the Euler second law, we can find the total moment acting at the center of mass here, which is defined by G, equal to the rate of change of the angular momentum about the mass center here. So imagine that this rigid body is formed by infinite particle inside. Let's say there is one particle here defined by mi, which is the mass of this particle, and then the radius from the center of mass to this particle is equal to rho I. So if we can find the velocity of this particle, then we can obtain the linear momentum by multiplying the mass of the particle I multiplied with the velocity of the particle I. When you take the radius cross with the linear momentum, you obtain the angular momentum for this particle I. So if you take the summation of all the particles from I equal to 1 to n, which is infinity in this case for a rigid body, then you can obtain the total angular momentum of this rigid body at the mass center here, G. You have learned how to use the relative velocity motion approach to find the velocity of the rigid body here. So let's say the velocity at the particle I here is equal to the velocity at the center of mass here plus the velocity at point I here that is measured with respect to the center point here. So this is in bracket of a small letter x, y, z, which means it's measured at the rotating frame. This is because the rigid body here has the possibility to rotate. So in this case, you will have the rotating effect, which is the velocity due to the rotation at the frame. It can be computed by ohm crossed with the radius from the point I with respect to point G. Ohm is basically the angular velocity of the frame here. This velocity component can be computed by using the omega cross the radius from point I with respect to point G here, and omega is the angular velocity for the body. The radius at point I with respect to G is equal to rho I in this case. Therefore, we can substitute the rho I here inside. Since we know that ohm plus omega is equal to the omega total, therefore we can convert these two terms into this. And the velocity at the center of mass is frequently written in this format, where you have V bar here. Vg and V bar here have the same meaning. Both of them are equal to the mass center velocity. So you can see that to compute the angular momentum at the mass center here, you need to compute infinite number of the velocity at infinite number of point I. So it is not practical to find the velocity at each mass at point I one by one to solve the angular momentum. So we need to further simplify this equation. Let's substitute the Vi here inside this equation. After you substitute the Vi inside, you should obtain this equation. And you can expand this equation into rho cross mv, which is this, plus rho cross m multiplied with the omega cross with the row, which is this. So we can rearrange this component into this by using the concept I cross j equal to negative j cross I. So if you switch the vector during the cross product, then you need to have negative. Therefore, you can see when you switch the v with the row here, then you need to take a negative. At the mass center, the summation of the mass multiplied with the radius will be equal to 0. Therefore, this component can be cancelled. Summation of the I particle from 1 to infinity can be rewritten into integration with respect to the dn. This conversion can be done by taking the limit where the n is approximate to infinity and the delta m is approximate to 0, which is very small. We have successfully obtained the angular momentum about the mass center in integration format. Let's assume the radius vector is equal to si plus yj plus zk, and the total angular velocity is equal to omega xi plus omega yj plus omega zk. So when you perform the vector triple product for this component, then you should be able to obtain this result. When you substitute the vector triple product into the angular momentum equation here, then you should obtain this result. Based on the definition, these three components at the diagonal term here in the ijk direction is equal to the mass moment of inertia ixx, iyy, and izz. For the simplicity, we also call this as ix, iy, or iz. Therefore, you can substitute the mass moment of inertia inside in the xyz direction. When you look at these three components, based on the definition, these are the product of inertia for the ixy, ixz, and iyz. With that, we can have the product of inertia for these three components. Similarly, you can use the product of inertia to find the iyx here, izx, as well as the izy here. So this is actually the angular momentum in the I direction. You can label this as hx. So angular momentum in the y-axis is equal to hy. Lastly, you have the hz. You can rearrange the hx, hy, and hz for the angular momentum in this matrix format. Hx here is the angular momentum in the x direction, which is equal to the ixx multiplied with the omega x minus with the ixy multiplied with the omega y minus with the ixz multiplied with the omega z. This is exactly the same with the hx equation here. So you can actually perform the same procedure for the hy and xz in order to obtain these two equations. In fact, we can diagonalize this matrix into much simpler format here by choosing the x, y, z axis here in the principal coordinate. By doing this, the product of inertia here will be eliminated equal to 0 if you choose a appropriate axis to compute the angular momentum. If you choose the coordinate in non-principal axis, such as this, let's say you put your x, y, z coordinate to be here, and you are going to find the angular momentum of this rigid body with respect to new axis here, then you will no longer obtain this, and you will obtain the product of inertia, which is non-zero. Luckily, for many engineering structures, we can easily choose the principal axis, such as the one here, x, y, z, in the principal axis for this thin disk. Therefore, we can always simplify the angular momentum calculation into this format. Lastly, we can further simplify this equation into this, where you have the angular momentum at the center mass at point G here equal to the Ixx multiplied with omega x in the I direction plus the Iyy multiplied with the omega y in the J direction plus the Izz multiplied with the omega z in the K direction. So this equation is very useful. Please remember this. Please remember that this equation is only valid when the coordinate axis that you select is a principal axis. So you have learned that you can compute the angular momentum at the center of mass for this rigid body by using this formula. How about to find the angular momentum of this rigid body at an arbitrary point, let's say at point P here. So you can do this by performing this formula. Take the Hg. You should know that the mv is the linear momentum. R cross mv is the moment of linear momentum about the point P here. So this is due to the translational motion of G here with a velocity v. So as long as the velocity here is 0, then this component will be cancelled, then your hp will be equal to hg. However, if the velocity at the center of mass here is non-zero, then you have this component and you need to compute it. These two equations are very useful in the kinetic analysis of a rigid body. Please make sure you master it. Once you find the angular momentum at the center of mass for this rigid body, you can use this formula to obtain the kinetic energy. So T symbol here means the kinetic energy of the rigid body. Since the rigid body here is not only doing the translational motion, but it also can rotate. Therefore, the kinetic energy is composed by the translational energy as well as the rotational energy. So translational energy normally you know is equal to 1/2 mv squared. You need to be careful since you are using the vector. Therefore, the dot here is actually the dot product between these two vectors. The V bar here indicates the velocity at the center of mass. So once you obtain the velocity at the center of mass, you can substitute inside, and you know the total mass of this rigid body. Substitute inside, perform the dot product, you obtain the translational energy. So we know that the velocity in the linear motion can be converted to the omega in the angular motion. Similarly, linear momentum, which is the mv in the linear motion, can be converted to the h, which is the angular momentum. Since the velocity here is at the center of mass, therefore the angular momentum that you obtain will be at the center of mass as well. Therefore, once you convert into the rotational motion here, you obtain the rotational energy by using this formula. So don't forget, the dot here is also dot product between the omega vector and the angular momentum vector. On the other hand, if you have a rigid body that you measure the angular momentum with respect to point O, and point O is an inertial frame. So you can compute the angular momentum by using this formula. Once you compute the HO, you can substitute inside this formula, and you can compute the dot product between the omega and HO here. And after you compute it, when you compare to this result, you will obtain the same result. So this formula is actually a simplified version for this formula. You can use either way to compute. So you must learn how to compute the kinetic energy for the rigid body by using this formula or this formula. When you use this formula, you need to be careful. The point O here must be selected carefully at a fixed point. This formula is only valid when the rigid body is pivot above the fixed point. If you use the general expression formula here to compute the kinetic energy, then you'd have no concern about this, because this formula can be applied for most of the case.